To get started, welcome to day 6 of Advent of Code 2024. We're going to get started here soon as the new puzzle drops. We've got 13 minutes. I've already set up my environment, so we are good to go, but it's always good to double check. It's day 5. We want day 6. And then, can we run it without error? So we are, let me do that. So we can get rid of that duplicate library. I think I need to update. There might be an issue with Homebrew. Or we will worry about that later. So while we wait, I just figured I'd share one of my other projects that I created. This is an implementation of Conway's Game of Life in Go. But the difference here is that it is using a grid in the terminal. So it's a terminal-based application, but it's a representation of Conway Game of Life. You can provide any seed you want to it, and it will iterate through it and create some interesting patterns and shapes. The grid has to be pre-decided, but my idea is I might be able to do something like this to visualize with at a later date, or use Fine, which is a Go desktop GUI builder library. But it's pretty neat. I'm excited about it. I want to do some more work here. I've got quite a few experimental things that I've been working on, just kind of my own time. Maybe we can dive into different specifics, but as of right now, we'll stay focused on Advent of Code, kind of see where that goes. So I'm excited to get started with everybody. Just waiting on the next group of the timer to start. So we will wait for that to occur. If anybody has any questions or comments, feel free to leave them. I will try to respond at least verbally, or I'll respond in chat. Try to be a little bit more interactive in the chat itself. So feel free to comment or ask questions as we go. And if you want to provide feedback or suggestions on the approaches, please do that as well. Yeah, so let's take a look here. Yeah, we'll let this run while we wait. Again, this is a Go terminal implementation of Conway's Game of Life. And just kind of a neat little visual while we wait. We can actually provide different seeds too. Let's see how I implemented that. The curiosity. We can provide a seed file, if I recall correctly. Yes. If I change this to SD star, and then I rerun this, not that, that was not it. This is it. Well, I guess I don't have the star seed here. That's unfortunate. Okay. Well, it can load other seeds. So don't have that example here, but pretty cool. So a couple of things that I did after yesterday's test. I ended up moving the index function I made to the common file so that you can, and I made it a generic so that you can take in any slice and it will give you back the keys with the indexes appropriately assigned so that you can look up the index of any value in a given map. Just kind of a quick helper function, quality of life, I guess, for myself, and make things a little bit faster because Go doesn't have some of these things built in by default. And so there's also another library I've been looking at. It's been a while, called Low. It's based on the JavaScript library Lodash, but it's called Low. And I didn't want to use any external libraries for this approach. I wanted to do everything myself. However, I may look at using this tool set in a future implementation. The reason why is because you have things like map, which takes in and you can do interesting things with. You can filter. You can get just back a flat map. You can reduce, right? It has all these helper functions here. But I've been a little hesitant because it does kind of do things in like a non-Go idiomatic way. Not that I'm a big Go idiomatic person. However, you know, yeah. So, right. So give it a few more minutes here. Got 7 minutes total. It's been a good day so far. Since it's the holiday, I've been taking time off of work on Fridays, but I am on call also tomorrow. So I will be on PTO on call at the same time. Don't know if anybody's ever experienced that or understand on-call strategy, but my team manages some applications that are highly important, and so we have to make sure they're up at all times, and they're implemented in Kubernetes. We have different checks and systems in place to make sure that those applications stay up at all times. But we have an on-call rotation just to make sure that if something does go bump in the night, we can take a look at it, resolve it, those types of things. So, I am on that rotation. It's a 24/7 rotation. So pretty much meaning that if something goes bump in the night, it's going to wake me up first, and then I have to engage the rest of my team. For what it's worth, I've heard some teams where they're on that every 4 weeks. I'm on this rotation once every 30 or something weeks. So that's pretty good. If you ask me, that's pretty low maintenance in the grand scheme of things. And so pretty happy about that. But I don't know if you've got anybody here has working for a company that they have some sort of on-call rotation. I'd be interested to know, what kind of requirements they put on you. Feel free to chat, put a message in the chat, or, maybe comment on this video later. Be interested to see what kind of strategies you employ. But the infrastructure that I work with primarily on my team is all structured around Kubernetes. So whether it's a service, an API endpoint, a user interface, we'll typically deploy those as pods in a Kubernetes cluster. And then we have redundant clusters geographically to make sure their apps stay up at all times. And then in addition to that, we use databases like MariaDB, other databases, but those are set up in a high availability master cluster, 4-node cluster. So we have some pretty highly redundant things, but still, if a redundant server dies, you want to bring that up as soon as possible so that you maintain your redundancy, right? Redundancy is there just in case something fails, not because, you want to make sure that you don't have two things that fail. I mean, it can happen in our system in a lot of cases too, where 2 of 3 could fail and we'd be fine. But once you lose one, you start to get concerned, right? So that's my on-call rotation right now. Again, I'd be interested to know if anybody else is in that boat or has been in that environment before. So I guess it's just part of the game, right? So I'd also like to know if there's anything that anybody else is interested in outside of admin of code. We're gonna dive in here on day 6, but if there's specific topics you want me to cover, like MariaDB, SQL, maybe PostgreSQL, MongoDB, OpenTelemetry, I'm open to other suggestions or things to dive into. I've got a wide girth of knowledge, I guess if you could say, across the industry, and be able to provide hopefully some insight into real world application, right? That's where I think I sit pretty well, is actually implementing these projects and getting them connect together. Just to kind of clear something up too with this YouTube channel. This YouTube channel was something that I created or the idea of Grepacks was created 10 so years ago, maybe. And in that, my father has been doing a lot of the videos on the YouTube channel up until recent. He's done a great job. Anything that is Krita or video editing or tutorial oriented, that is Red Feather. That's my father. He does those videos. He still does some from time to time. And anything coding or software related, such as admin of code, that's been me. And we've kind of worked together with this channel, kind of making it, kind of back and forth, a variety of content. But it's really all in good fun, right? So if we're having a good time, it's like, why not continue this process? We've got 2 minutes left. So I'm going to just try to fill the air with some what they call mouth service or lip service. So if you guys have a question, feel free to ask. I can provide more details or provide more information. There's a chat window there. I'm all ears. Well, here, we'll look at this some more. So this implementation here in the terminal uses, I think it's ncurses, but it's an implementation of building grids and graphs natively in a terminal. And so I want to be able, I might use this for some sort of implementation later where we demonstrate some sort of grid process, whether it be like Dijkstra's or some sort of pathfinding algorithm. I thought about doing the word search problem we had the other day on like day 4, I think it was, of kind of implementing it in a unique way. And maybe if I have some time, I'll come back and revisit some of these puzzles. But right now I'm between work and being on call and doing these live videos at midnight. I've been kind of getting pretty tired. Yeah, so this is Conway's Game of Life. It's implemented, or I wrote it in Go, and it has the ability of receiving different seeds. There's a wiki. Let me not be distracted. Got 20 seconds. All right. Yeah, there's a wiki article that has all the seed files, and so you could download a seed, plug it into this platform that I have, and it will do that natively in the terminal. So I think that's pretty cool implementation. It doesn't require any desktop forms. All right, day 6 is ready. Day 6, Guard Gallivant. The historian uses their fancy device again, this time to whisk you all away to the North Pole prototype suit manufacturing lab. In the year 1518, it turns out that having direct access to history is very convenient for a group of historians. You still have to be careful of time paradoxes, and so it will be important to avoid anyone from 1518 while the historian searches for the chief. Unfortunately, a single guard is patrolling this part of the lab. Maybe you can work out where the guard will go ahead of time so that the historian can search safely. You start by making a map, your puzzle input of the situation. For example, the map shows the current position of the guard with this caret, Okay. To indicate the guard is currently facing up. From the perspective of the map, any obstruction creates desks, chemical reactors, etc. are shown as the pound sign. Lab guards in 1518 follow a very strict patrol protocol which involves reportedly following these steps. If there is something directly in front of you, turn right 90 degrees, otherwise take a step forward. Following the above protocol, the guard moves up several times until she reaches an obstacle, in this case a pile of failed suit prototypes. Okay, here. Because there is now an obstacle in front of the guard, she turns right before continuing straight in her new facing direction. Here. Reaching another obstacle, a spool of several very long polymers, she turns right again and continues downward. The process continues for a while, but the guard eventually leaves the mapped area after walking past a tank of universal solvent. By predicting the guard's route, you can determine which specific position in the lab will be in the patrol path, including the guard's starting position. The position visited by the guards before leaving the area are marked with an X. When does it go down? Where did I miss that rule? Oh, it's because it's always 90 degrees. Got it. Okay. The process continues for a while, blah, blah, blah. By predicting the guard's route, you can determine which specific position in the lab will be in the patrol path, including the guard starting at the position. The position visited by the guard before leaving the area are marked with an X. In this example, the guard will visit 41 distinct positions on your map. Predict the path of the guard. How many distinct positions will the guard visit before leaving the map area? Okay. So we can do that. Let's take a look at our puzzle input. I haven't typically done that, but I'm going to go and look at it and see, okay, there's a lot of input here. So there's kind of two ways in my head that we can go about this. The first way is if we take this grid, we can just step through every location, right? We can crawl up until we hit a position. Here, let's move this into freeform real quick. Yeah, we'll create a new board. And we'll call it AOC Day 6. Create some text. Put that at size 96. Paste that in here. That did not work. It's okay. Maybe we'll go a little bit smaller anyway. 48. We'll create it as black. And then the show fonts, we just want like a regular, like a Monaco, monospace, Menlo. We'll try Menlo because I think Monaco doesn't work on my iPad for some reason. Right. And then if we pull up the iPad, we'll just kind of step through this. I know I'm not going to solve these like in fast time like some of the other guys, and that's okay. It's not really my reasoning for doing this, but we can talk about the two approaches here. So the more like, I guess you could say like brute force approach is if we start, well, I guess okay, this is fine. This isn't the starting position, but we'll just use that as an example. If we start here, we can just simply turn right and go here, then here, then here, then here. And every time we get to a position, we can then create a map of the XY position essentially. And then we know we're going to turn right. So we're going to go here, 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 here. And we're going to come back here. And then it's going to go here. Then it's going to go here, and then it's going to go here. The reason we're going to use a map is because this is going to get cataloged again. Come back here, come back here, come back here, and eventually come off the map, I think here. And so as we do that, we can catalog all of those locations anytime we hit a pound sign. So I think that is one way to approach it. The other way is that we can pre-scan, which I think we're just going to go with that approach and kind of see where we're at as far as speed. But I think we can be a lot more performant because we actually don't need to know when we're at this position, right? We don't need to know and visit every single location along the way. We just need to know on this row to our right, where is the next closest pound sign, right? And then what we can do is we can do a math calculation on how many rows we visited here. But then we have to figure out the visited, so that's kind of interesting. But then also here, and then we could just jump down and then same thing here, jump, here, jump, etc. Kind of going through this whole process. And so we could jump to those specific locations, but I think that's probably overkill. And it seems like that might be fraught with an issue. Although it probably is more efficient, I would just have to, since we're doing a distinct set of points, I would have to like catalog the range of points with each hop and then make sure we're not double counting those points. Maybe we would somehow catalog them by marking them with an X or something, but we don't actually have to mark the grid. So let's implement the first solution that I talked about. So where we are stepping it one at a time. I think that'll just be our initial approach here. So if we take our input for our test, we grab this and we're going to put this in our, let's close all of these and we'll put that in our test.txt, and the test result is going to be 41 because we want those distinct positions. And so there we go. And if we run our test, we can see it's not 41. Okay. So then our next step is we have this input and it's already broken, or it's a single matrix. So we're going to go ahead and read in S, and we're going to read it into this matrix library that I created. And our separator for it is just empty spaces. So we're going to get rid of this pipe here. And if we do a so we just double check to make sure our parsing is working. Invalid syntax. Oh, it's not a int. It is just a set of strings. So that's done. All right. Got this nice little grid printed out here. Beautiful. So now what we want to do is we want to find the starting position. And actually, I'm going to find the starting position and I'm going to just replace the caret, if you will, with just a period, right? So we're going to, for, I wonder if the starting position is always the center. That's a possibility. It looks like it's probably just the center of the grid, but just because I like to create things a little bit more generically, let's assume that it's not always the center of the grid. And so we're going to do this. And we'll simply do this. And then this is an equal sign. And then we'll say if C equals, what's the caret? There we go. we're going to use a slice of int to represent these. Center equals, or C, sorry, center yeah. And we're going to do I comma j here. So that will indicate our center. And then we're going to break out of here. Yeah. Okay. So now that we have center, we're also going to set m comma, or I'm sorry, I j equal to dot. That way, if we run through the center again, it's not some weird character. Actually, I don't think it really matters, but we're going to go ahead and run with that. So then now that I have my center, we need to say our, actually, we'll just call this cur. Actually, let's call it position, POS. So that's our position. And we can say while or for sub 0 greater than 0 and position 0 less than the length. Okay, not what I wanted autocomplete. The length of m minus 1, or length of m. And then we do the same thing but position 1, and then m is just the first record. So while that is true, then we're going to keep looping. So that way, if we'll know whenever we exceeded or have gone outside the bounds of a position. So then if there's a better way to do that, but I'm going to leave it for that for right now. So as long as this is true, we're going to continue to move our position. And so our direction is going to be the direction is going to be the direction that we want to head in. So it is always going to be we're going to call this a slice of ints, and we're going to call matrix dot dir down, matrix left, actually we want to start with matrix dot dir up, matrix, because we're going to go to the right, and then we're going to matrix down, and then we're going to do left. Okay, so these are our directions, and we're going to keep going through that. And then our So our direction is going to be an index of 0. And so we can then say position sub 0 is going to be plus equal directions sub 0 I'm sorry, this is going to be subdir sub 0, and 1 is going to be the same thing. So if it's negative, it'll point at negative. If it's positive, point at positive, and we're gonna keep iterating through that. Just realize that actually I'm going to move this to here, and we're going to say if this, then break. So we know if the new position is outside, that we're done. Then we'll say if m sub position 0 sub position 1 equal a pound sign, then we know that we need to switch directions. So if dir equals if dir equals 3, then dir equals 0, else, wrong button, there we go. So we're going to increase our direction. We're going to move to the next one in the index. Yeah, so we're going to move to the next one in the index. We're basically looping through this, and anytime we get to the end, we're going to come back to the beginning, and that's going to keep our loop position correct. So only if that is true, then we're going to catalog that. Otherwise, we know that we are at a position that needs to get cataloged. And so the easiest way for us to do that is we can create a unique positions, which is just going to be a map of, we'll just call it string to ints to catalog the we'll call it that. And so if that is the case, we'll continue back up to the top and we'll continue on this process. If it's not the case, then we know that we're on a dot essentially. And so we will just simply catalog that as we'll just do it this way, and we'll call it position 0, position 1, and we'll do a plus plus. And that'll be it, and it'll keep looping until done. And then our score will be the length of unique. So we keep a map of the specific locations, loop through that, and that should be done. So let's see what we have here. If we run our test, actual 0, expected 41. Test file is in here. It is saved. This should be less than 0, I think. And this should be greater than. This should be less than. And this should be greater than. I really should switch to other syntax style. Okay. I think this should be an or. Actually, this should be an and. It's I'm too tired, guys. This is not funny. Yeah. So if position 0 is less than 0, or position 0 is greater than the length of m, this should be an equal. Okay. So what do we do wrong here? So we've got 5. Our expected is 41. We should catalog the initial visit here, but I don't think that is our problem. Yeah, that's 6. So let's see how this is working. So dir up is 0. Oh, are these -1? Do I have these inversed? The dir up should be. Yeah, I think I had those wrong. Okay. So up is -1, so we're going up, and down is +1. And so if I go back here, and m is the row, 0, 1, 2, 3. If dir is 3, it's 0. That's the one thing I don't understand. Okay. 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 Am I not cataloging this? If this is true, Well, see what we get here. All right, we're at 6, 4, 5, 4. And that's how we get to 11. Okay, let's take a look at this real quick. So we go 6, 5, 4, 3, 2, 1, 1 of 4. But then we go 0, 4. Why do we go 0, 4? We should not be going 0, 4. Okay. So we are going 0, 4. Because you're right. So we're checking that position and then we're saying, hey, it's there. So what we actually need to do is the inverse of this here. We'll do it this way. There might be a better way, but I think this will solve our test problem. Or just make things worse. Oh, okay. I see. This needs to be after we set the direction, before we reset the direction. So that's not going to work. We just created like a recursive little loop here. Fun stuff. Yeah. Okay. This should work. Awesome. So if we take our input now, did we grab our input yet? No. So if we get our puzzle input and we put that into day 1 or 1.txt, day 6, 1.txt, and we come back and we run that. Not the right run command. There we go. Oof. Index at a range 0 would link the 0. Oh, that's because of the part 2. That should be our score for part 1. Yeah. Awesome. Part 1 is solved. Let's take a look at part 2. Let me close this. No, that one's fine. Let me close this out. All right, part 2. While the historians begin working around the guards' patrol route, you borrow their fancy device and step outside the lab. From the safety of a support closet, you time travel through the last few months and record the nightly status of the lab's guard post on the walls of the closet. Returning after what seems like only a few seconds to the historians, they explain that the guards' patrol area is simply too large for them to safely search the lab without getting caught. Fortunately, they are pretty sure that adding a single new obstruction won't cause a time paradox. They like to place the new obstruction in such a way that the guard will get stuck in a loop, making the rest of the lab safe to search. To have the lowest chance of creating a time paradox, the historian would like to know all of the possible positions for such an obstruction. The new obstruction can't be placed at the guard's starting position. The guard is there right now and would notice. In the above example, there are only 6 different positions where a new obstruction would cause the guard to get stuck in a loop. The diagram of these 6 situations uses 0 to mark the new obstruction and a pipe to show where the guard moves up, down, to show a position where the guard moves left, right, and plus to show a position where the guard moves both. Option 1 puts a printing press next to the guard's starting position. Option 2, option 3, 4, 5, 6. Doesn't really matter what you choose to use as an obstacle so long as you and the historian can put it into the position without the guard noticing. The important thing is having enough options that can find one that minimizes the paradoxes. In this example, there are 6 different positions you could choose. Okay. You need to get the guard stuck in a loop by adding a single new obstruction. How many different positions could you choose for this obstruction? Okay, so you could brute force this, kind of tacking onto what I did previously, but I think the time complexity would be too large. What I mean by that is that you could just place you could run in each iteration. So let's see, this took 0 seconds. I could. All right, so this is a lot of input, but what I could do is I could go through and first I have to know if I'm in a loop. That's problem number 1. Am I in a loop? I think the way we can determine if we're in a loop is if I ever revisit, I can catalog every node and the direction that I approach it at. And then I could say if I ever revisit that node again, I know that I'm in a loop. The direction is important because if I, like, say, hit this one and I come down to here, but if I also hit this one and come over to here, the direction in which I approach that one dot is going to matter, right? Does the direction matter though? Because I can only approach this one from one side. No, I could approach it from the top too. So yeah, but this one, I'm not positive the direction matters, but that's okay. So what I could do is I could just start filling this in, but as you can see, there's a number of dots. And so we're going to have to go through 431 iterations, and then each iteration is going to have to run to fullness in order for me to determine whether or not we're in a blocking condition or not. So I think while we could do that, I think that is kind of out. We can try it and see, but essentially it would be starting in position 1, grab the matrix, pretend like there is a stopper here, run everything 2, 3, 4, 5, etc., and just keep iterating through until we've got every possible iteration of this thing other than starting position populated. And then for each one, I mean, I guess we could concurrently check, but let's work on the loop detection part first. So in the first example, because we weren't trying to create ourselves into a recursive loop, we knew that we didn't really care so much because our input was good, whether or not we were in a loop. And so what I would like to do is if we're here, yeah, so we can create a yeah, let me create a part 2 real quick. Let's actually separate this out. We'll go with that. We'll come back here and we'll go with that. Okay. So what I want to do is I don't care about the unique count position. What I care about is if I'm in a loop. So we can use this to our advantage. And what we can do is we can say, okay, anytime I reach this, I'm going to catalog that position. And I'm going to catalog one other thing here, which is the direction. So what that means is that if I hit a pound or an obstacle, I'm going to catalog the direction that I'm coming from as my unique index map here. And so my goal is not to do a pure count, but it's to say, if we've encountered that before, we know that we're revisiting from the same direction to the same hash that we're bouncing off of, so that we are in a loop. Because if we visited once and we're visiting it again, we're guaranteed to be in a loop. So that's our, we're not going to fatal here, but that's our loop condition, right? I guess we can score plus plus here and then break, right? Okay, cool. So now we know that we've got a score that we can increment. Cool. And we're going to return score here. Okay. So now we know how to increment our score, and that's anytime we get through that uniqueness. So our answer here let me how do we want to do this? I kind of want yeah, I kind of want to just pass these two things in. And instead I can return true here. Return true. Yeah. And then Right. So we can do this. And so now we can use a function. And with that function, we can say if has loop, and we can call with the original position and the matrix, we can do score plus plus. Okay. So now we have our original matrix. So now let me create. I'm going to generate a unit test for has loop here. And if we look at our test input, we're going to create a I should just trust what I'm doing here. So this can be optimized. Let me grab. Yeah, okay. So if we take our test input and let me instead do this, and we're going to call this 1. And for our input, we are going to use a test2.txt. We'll call this B2. I was trying to get away from this, but actually I think in this case it makes sense. And we'll rename this to test2. And what we're going to do is we're going to simulate this of, I think that'll create our loop. So if we run this, our second test looks like it's looping, but I didn't identify the loop properly. Let's see here. Input B2 function part 2, and part 2 I call has loop, and it's going to loop through, and yeah, so I'm rechecking over and over again. So why did this fail? Yeah, so we're definitely looping. Why did this not return true? am I missing here? What did I forget? I realize the pacing is slowing down a little bit here. But I think we're almost there for at least the identifying of the position. And so this should be just, whatever the position is of this and the direction added onto it as the key, which is the same that we're using here for that. And so that's not getting reevaluated every time. The direction's fine. So any suggestions? Any thoughts? I realize this is probably not the cleanest approach, but checking 6, 7. So if I turn, oh, I modified the wrong file. Would have been helpful if I noticed that earlier. Okay, great. So now we know we have a function that will detect our loop. If there's an issue, we can look at further optimizing that later. So the next approach is really, the question is, can we just brute force it, right? So if we did something like for every row for every column, right? And we say if m sub r sub c equals we'll go ahead and say that, and actually I'm gonna not do this. I don't think that's actually that, it doesn't need to be done. So anytime it's this, we are going to this is range R, and this really should be I and J, and this should be I. Actually, we could just say C. Yeah. Okay. So if this is true, then we'll call it new equals to slices dot copy or clone. And we'll call it M. And then we'll say N sub I sub J equals to a hash. So, and then we're going to say temp, or we'll call it M's tests. We'll call it tests, which will be a slice of matrix.strings. Okay. And then N will go into, N will equal to append tests N. I think, right? So we're cloning the matrix.strings. Sorry, tests equal to append tests. And then for test in range tests test. So we're going to loop through all of these, and for every possible scenario, we're going to check and say, okay, what is our possibility? How many of these can we actually fail on? So let's just see if we can get this to run in our test case for the desired result of 6. So we're generating all of these different maps, and our actual is 91 different variations. Interesting. So let's go back to our request and see. There are 6 different positions you could choose. Only 6. Okay. Fortunately, they're pretty sure that adding a single new obstruction won't cause a time paradox. They like to place the new obstruction in such a way that the guard will get stuck in a loop. To have the lowest chance of creating time paradox, the historian like to know all of the possible positions for such an obstruction. This new obstruction can't be placed at the guard's starting position. The guard is there right now, and would notice in the above example, there are only 6 different positions where a new obstruction would cause the guard to get stuck in a loop. The diagram of these 6 situations uses O to mark the new obstruction, to show a position where the guard moves up, down, where the guard moves, option 1, but prints. Okay. So let's do, I'm going to do something just to kind of get us an idea of what we actually have cooking here. We're going to do a, I'm going to do the test dot pretty. I'm going to print it out, and then I'm going to do time dot sleep, time dot second times 3. All right, we'll say actually just time dot second. That's going to be more than enough. We'll call this 10. I'm worried that the underlying slices are still being modified as references and they're not actually being copied. And so an actual copy of the slice would have to be done. And I think this will kind of reveal that to us, because okay. Why is my grid fully populated with hashes? What happened? What did I do? What did I do? What did I do wrong here? Okay. So if theoretically, hold on. Yeah, we're not doing the center one, which is good. Okay, so I think what I need to do is, yeah, okay, so it's a shallow copy, right? So actually I would need to clone each of the sub values as well. I could just do it in here. It's fine. Um, it's not great, but it's fine. So what I can do is instead, yeah, I could do oh, this is a lot of disgusting work. I'm just debating on whether or not I want to go through this whole like clone process here. It's unfortunate that we don't have like a deep clone. Because it's a shallow clone, right? So the elements are copied using assignment. This is a shallow clone. The results may have additional unused capacity. It returns a copy of the slice, but it's a slice of slices. So I think that's the underlying issue. So let me just do this. Let me go to strings and I will create a function called clone directly on here, and we will return strings. There's a lot of extra looping. So we'll call this n, and we will say more or less n equals to append n slices clone r and return. That wasn't as bad as I thought it was going to be. So then if we come back here, if we make n to be m dot clone, let me try this again. Could probably make it a little bit quicker than 10 seconds, but yeah, okay, so we've got we got different grids now. Okay, so that's what I wanted. So now we know that that's working properly. We don't have to print out each one. So we can get rid of that. And oops. Now if we rerun this, we should get our expected is 6, our actual is 0. Okay. Let me make sure. Okay. So let's go back to this and let's take out the sleep. That's not what I'm expecting. Okay. Okay. Wait a second. Oh no, that is only one over. Okay. 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 Yeah. Yeah. Okay. I'm just kind of looking, watching it move, watching it move. Okay, I think I have an idea of what the problem is. Yeah, so that is in here. So, okay, I thinking through this, I think we have one other issue, which is the position that I create up here. We're passing in here, but I think it's getting modified under the sheets. So I think what's happening is that value is changing. Yeah, okay. So there's that. So the test pass. So now what we're going to do is we're going to just see if we can just kind of brute force it, right? So let's see if that will work for our... Oh, we probably shouldn't print all these grids out. That is not going to be good. Okay, well, apparently I'm still printing them. All right, let's see what this produces. That's part one. Let's see how long it's going to take for part two. Alternatively, we should get rid of all these checking messages. That's just going to make things run longer. Let me see if I can get rid of those. We don't need them anymore. Try again. One of the things we could do is concurrently process these. So we could run some sort of concurrency and do them in parallel. But this is kind of the really brute force approach here. 1909. That's interesting. Awesome. All right, we solved day 6. So I know for a fact, well, I'm pretty confident, let me rephrase that we can do this in a more optimal way. But let's kind of recap here and talk about the approach. So part one was we ended up with a, well, let's go back and look at the actual puzzle. And actually, we'll go through it this way. So part one was we were given a grid, and this grid had some obstacles in it, and we had a starting point. And that starting point was always at the center. In this case, it's not at the center in this diagram, but you get the point. So our center was here, our starting point. And anytime we run into an obstacle, which is notated by this hash character, we would make a 90-degree turn. So we would turn here, and we had to catalog every step along the way. And we wanted to get the unique steps. And so we would catalog them, etc. Go this way, 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 until you get off the map. Once you are off the map, you know that you did not have an endless loop. And the idea was that you would count all of the unique positions. We did that by creating a unique map. And as we step through each position, if it wasn't a bumper, we would go ahead and catalog it. Now, we probably could do this with just maths. But the interesting thing is that if we did it by calculating like a hop between here, let's erase. If we calculated it as a hop between here to here, we would have to somehow know that these are visited along the way. I think we could do that. That's actually an option here that we could explore, and so on and so forth in problem number 1. Problem number 2 was a little bit more complex in that we still had the same grid, but it knew that this was not an endless loop. And so we had to determine where we could place a hash in this grid, like here as an example, that would cause this to then become an endless loop. And so we had to detect the condition where we were constantly in a loop like this. So this would create a endless loop condition. And so the way we did that was, instead of counting each position along the way, what I would do is I would say at this position, when we found this obstacle, what direction were we approaching that obstacle at? And if we ever hit that unique condition again at all, we knew that we were in a loop. So that's how we determined that we were in a loop. So that is pretty straightforward. The thing that we needed to do is, with a given input, we had to not just figure out one, but we had to figure out every possibility. So I took just a brute force approach to this, and I said, okay, well, we'll start at position 0, 0, and we'll try it. And then we'll go to position 1, 1, and we'll try it. And position, 0, 1, 0, 2, and then 0, 3, and then we'll try it. And I would do that for every single combination. And every time we would come up with one that would be a blocking condition, we would increment our counter. And that's how I approached the problem and solved it here. Is there a better solution? I'm fairly confident there is. For instance, if we know we can do something, I'm going to guess where we can predict or look at this and say, okay, we don't need to try every combination. We could probably, actually, I know the answer. So the one more optimal solution is we run the initial algorithm, which gives us all of the places that we've visited. I didn't see this until just now. All the unique locations that we visited to get into an exit condition. And then instead of trying every single possibility, we know that these, since we never visit them in the original solution, do not even need to be checked, right? Since we know we're not going to path there initially, we can just eliminate them. Same thing here. Technically this was in the center, but I think these were also not visited at all in the initial. These are not visited. And so we can optimize this algorithm by only looking at the places that were visited based on the initial starting position. And we would eliminate all of these calculations here. So actually, if we can, I would like to see if we can implement that. Actually, those were probably in the initial. But I want to see if we can actually implement that real quick just to kind of see if we can make this a little bit more optimal. At least cut down on the number of, attempted paths that we have to do, right? So, we've got 7-second processing time here. So what we can do is I can sub function this, and I can just say and we can pass in POS, which is our slice of ints, and our M, which is our matrix dot strings. It's a little bonus here. And so now we can call get visited, and we'll pass in those two things. And this has to be a whatever our unique is, which is this here. Yeah. Okay, so part 1 should still work if I rerun these tests. Missing return. Oh. Yeah. Okay. Yep. Okay, so we got that. So that is leveraging just a subcomponent. And then if I go through this process of first, if we call get visited, and we do a slices dot clone of POS, and we know that this doesn't actually manipulate the matrix, so I think we'll be okay. And so what we can do is the visited, that's a bit of a problem. So I don't actually have the X and Y position here. I have for the key. I could split it though. That's fine. So if we actually and then instead go from visited, and we can get rid of this loop and this loop. Oof. I can make this more efficient, but call this K. Yeah, and then we can do A to I, parts sub 0, and P2, part sub 1. And then this is P1, P2, or we can give it I, and then J, and we'll call this I and J. And I'm going to ignore the errors because I'm an awesome programmer. Yep, we don't need this anymore either. So same results, but executed in 1 second versus 7 seconds. We could probably go through a lot more benchmarking there, but we reduced our overall footprint of things to look at. Now, this I'm not a big fan of. I would change this data structure a little bit more so we're not converting in and out of these objects. But I think for now this works just fine. At least to prove the point. We can make this a little bit more efficient. Perhaps I'll do that off stream. But I thank everybody for joining tonight. If anybody has any questions or comments, feel free to ask. This went pretty well. We got done a reasonable amount of time. I'll clean this up and maybe do a review tomorrow on some of the optimizations, but I was glad to solve it. As always, we'll be continuing Advent of Code 2024 as long as I'm capable of doing it. I appreciate everybody for joining the stream. If you could like and subscribe, I'd greatly appreciate it. Y'all have a great night. Bye-bye.